I see Kelvin is in attendance tonight. Kelvin is the little robot in Tom's screen there, the mascot of the North Carolina Science Festival.
Kelvin.
And one of our mascots to our talk.
That's cool.
Well, I mean, it's 1 minute after 7 according to my clock. So I think we might as well get things started if everybody's ready. So, well, I'll start us out. I'm Stephen M. Desch from Guilford Technical Community College. I'm here to introduce our guest speaker tonight and kind of moderate things at the end of the talk. We'll start out with just a few thank yous to people out there who've helped us out and get this set up. So thank you to our GTCC Foundation, the finance department, the marketing department for getting all this set up, getting all the word out there, and getting all these people that I see still coming in to join this talk. What else? Well, thank you, of course, to Tom English as well. He's our Cline Observatory director. It's under his oversight and because of his shepherding of our programs that makes it possible to keep having high-level speakers like tonight come to our campus, both physically and virtually. And I know our students in our community appreciates all these opportunities. Quick advertisement for the Cline Observatory, since we mentioned that. We continue to have our public events on public nights on Friday nights. So if there's any students out there, of course, you know that. And you'll need to get out here at some point on a Friday night to complete your observing projects. Hold on, I got some noise out here. Sorry. And for anyone else in the community who wants to come out and look through some telescopes, we're open from 7 o'clock to 9 o'clock on Friday nights. Not for the lunar eclipse, though. So the lunar eclipse coming up this week. You'll need to watch that from home on your own. All right, but you don't need special telescopes to see that. So come out and see us sometime. All right, well, let's get on, I guess, to our guest speaker. A guest speaker with a suspiciously familiar name, but no relation.
I had it first.
He did have it first. He beat me to it by a few years. So I appreciate him letting me make good use of it as well. So it's just one of those kind of cosmic coincidences that the universe produced two people of the same name kind of doing the same thing. We've known of each other's existence since our college days. Never actually met face to face, which may, be a good thing for the universe. You never know what happens when you get two identical people in the same place at the same time. So we were lucky to have this opportunity. Well, I mean, the opportunity is because of a global pandemic, but it's kind of worked out well for this anyway. Yeah. The idea for it actually came out of a couple of chance occurrences, a conversation Tom English was having with a student and a chance encounter with my name in a magazine article in Smithsonian. And we kind of put two and two together and thought, well, our students are studying the formation of the solar system right now and exoplanets. And well, this guy with a familiar name, he also studies the formation of the solar system and exoplanets and such. And well, let's get these two things together. And so we reached out, and he was kind enough to accept our invitation to come on this wonderful virtual platform and tell us about the interstellar visitor we had a few years ago, Oumuamua. I hope I said that right.
Good for me.
So it's our pleasure to welcome Dr. Stephen J. Desch, astrophysics professor from Arizona State University. And I'm going to turn it over to you now, sir, and take it away.
Right. Oh, thank you so much. And I am just tickled pink to be here for the reasons that you described too. There's such a coincidence between the name. I've wanted to see what you look like for a long time, and I hope we do get to meet in person sometime soon. But I'm happy anytime I can talk about this object. I think this is such a fascinating object. Oumuamua, the first interstellar object discovered to be going through our solar system. And what is it? I'm going to try and convince you that it is a piece of an exoplanet. And so, in a sense, it's the nearest we've ever gotten to an exoplanet. So that's the theme of the talk. I'm trying, there we go. Okay. All right. So some things about it. It was discovered. Here's the image of it. They're tracking the object. The stars are trailing. It was discovered using the Pan-STARRS telescope array on Haleakala, and it was found in October 2017 after it had come by the sun and was making a close pass to Earth. This was an image from a follow-up observation, but it was the first object whose orbit clearly had it, coming from outside the solar system, and it's on its way out of the solar system now. First, clearly interstellar object from beyond our solar system. There's a few comets that get a kick from Jupiter and just barely make it out, but this one is screaming through our solar system. And as such, it was named because of its discovery on the Haleakala. It was given a Hawaiian name in honor of the indigenous peoples, and the name loosely translates to scout or messenger, because it was the first object from outside our solar system to be confirmed to come through here. So there were a number of mysteries. I'm going to get into these in a little more detail because it's not just a comet. Comets were expected. We know that our solar system ejects comets, and there should be comets from other solar systems coming through. But this one was found in only, it seemed like a few years. So there must be something like 10 to the 15, really 10 to the 16 objects for every star in the galaxy. And that just seemed like a ginormous number, higher than the numbers that were expected. And it entered the solar system at a velocity which was a little weird. I'll explain that. It pushed away from the sun a little bit too much. It had some slight deviation from its gravitational orbit, and comets do that, but this one was doing that much more than comets. It definitely had this crazy shape, either a cigar or pancake, we don't know, but it would vary in brightness by a factor of almost 10. And that's just really hard to explain unless it's a tumbling object with a very elongated shape, more elongated than any object in our solar system. Unlike a comet, there's no dust, no carbon monoxide was observed. And so just a bunch of weirdness. It's kind of like a comet, but not a comet. And so what is it? And what I'm going to try and convince you is that the behavior of this object is exactly consistent with what a piece of the surface of Pluto would do if you were to throw it past the sun. And if it were made of frozen nitrogen, which is what covers Pluto's surface. And I want to show you that our solar system actually ejected about the right number of fragments, like Oumuamua, early in its history. And if other solar systems did the same thing ours did, then that would explain the existence of so many objects like this. So the conclusion of my talk will be that Oumuamua is a piece of an icy exoplanet that passed by Earth. So I don't think this animation is going to work, but this was a cool animation where it shows the comet's trajectory. It comes in from above the plane of the solar system, kind of from the direction of the star Vega. And it actually swung by the sun on September 9, 2017, and made its closest approach of only 0.25 AU, or astronomical units. That's the distance between the Earth and the sun. Mercury is at 0.4 AU from the sun, so it went inside the orbit of Mercury and then swung by and made its closest approach to Earth on October 10, 2017, and where it was only about 0.16 AU away from Earth, and then was observed soon after that, and continued to be observed by telescopes, including the Spitzer Space Telescope, which can see infrared light, as late as November. But by this point, it is already past the orbit of Uranus, almost Neptune, and it's on its way out of the solar system. And it hasn't been observable for years. It's just too faint for us to see. So Everything that we know about this object was collected in those few months, and now we're trying to piece together what it was. If you were to look at its position in the sky, this is a kind of cool demonstration of, it's approaching from the direction of Vega, which is a special direction in the sky called the solar apex, which I'll explain. But as it got closer, the Earth's orbit gave us different perspectives that made it appear to swing around. And then, of course, it went by the sun. The size of these bubbles depict the size of it in our sky, although we never did see it as anything but a dot in any telescope. But it would have been bigger at its closest approach, and then finally, made its way out of the solar system and is on its way out in that direction towards Pegasus. So that solar apex direction is the direction in the sky towards which the sun is moving. So we have to remember that the sun is part of a galaxy of stars. And so there are stars in every direction, and they all have random velocities, but they are also all moving around the galaxy, orbiting together. And so there's sort of an average velocity of stars in our neighborhood, and the sun has its own random velocity with respect to that average velocity. And the sun's random velocity is sending us in the direction of Vega. And so some stars are moving in different directions. Some are moving towards us extra fast because of the sun's motion. Some are not. But on average, if you look in this direction of the sky, you would see the motions of stars moving away from this point in the sky, kind of like raindrops that you're driving fast through in a rainstorm. So this is a special direction, and it tells us that this object kind of was moving with the average velocity of stars in this part of the galaxy. I'll get to that some more in a minute. But this is one of the odd things about Oumuamua, is that it was moving very close to the average velocity of the stars in our vicinity. So we call that average velocity the local standard of rest. It is not at rest. It is a frame of reference that's moving with the average stars. And so it's moving around the galaxy at 250 kilometers per second. But on average, stars in our vicinity are, moving with that velocity plus some random velocity, like I've depicted here. Some are moving fast, some slow. And on average, the stars in this part of the galaxy are moving with random speeds that are on the order of 20 or 30 kilometers per second. This is kind of like the difference between the motions of atoms in a gas and the motion of a gas. You have, because of high temperature, atoms in a gas will be moving at random speeds, and directions, but typical speeds, kind of like the sound speed. But then you could have this balloon of gas and you're just moving it in a direction. So that's the same sort of idea. So we have this local frame of reference. The sun is moving with respect to it at about 18 kilometers per second. And Oumuamua came from the direction of Vega at about 26 kilometers per second, but most of that was because the sun was moving towards it. So it was actually moving towards the sun with respect to this local standard of rest at only about 9 kilometers per second, and the estimates are 3 to 11 kilometers per second. So kind of a slower speed relative to the local standard of rest than other stars. And so this was one of the things that was thought to be unusual. And I just want to give you a bird's eye view, not the 30,000 foot view, the 30,000 parsec view of our galaxy, but the parts of the galaxy we're in is about here, and stars in this vicinity are orbiting around the galaxy. And we are kind of in a spiral arm here, but there are other spiral arms of our galaxy, and stars tend to move in and out of these spiral arms. But most stars are born in the spiral arms. That's why they have the brightest stars, because the brightest stars don't live long, so they end up where they were born, and end up dying and exploding or whatever before they move away from the spiral arms. So the spiral arms are where the bright, hot, young stars are. And we have been going around the galaxy for 4.5 billion years. So we've gone around the galaxy about 20 times and gone in and out of spiral arms. Okay, So besides the velocity, one of the other weird things about this object was its light curve. So this is a graph of the magnitude, or how bright it is. It's bright as you go up and dimmer as you go down, versus time. And over the course of hours on different nights, it would go from bright to dim, bright to dim, and do it quasi-periodically with a spin, a rotation rate of about 8 hours. And yet it was going from 22nd magnitude to 25th. It's a variation in brightness of about a factor of 10. So it was, it's very hard to explain that as saying this is an object that's very white on one side and very black on one side. It's probably the same color all around. And so if you accept that, then it has to be one of these two shapes. Now, unfortunately, the first shape that was tried was the cigar shape. And certainly if the cigar is tumbling like a pen, you can see it would present more area this way, less area this way. So it would be 10 times brighter here than here. And this is the artistry that got into the mainstream media. And so everybody thought of a cigar, which probably makes you think of Rendezvous with Roma. But in fact, just a month later, this shape was hit upon, and a pancake-like shape. And I know every time this picture is commented on, it's one of two things. It's either steak or Millennium Falcon, depending on how hungry someone is. That's what that looks like. But anyway, a coin also will, if it's tumbling or rotating, will present different areas. And this actually fits the light curve data a little bit better, especially this weird dip this way. So it's inferred to be a pancake shape where the thickness is only 1/6 of the width, but it also is not very big. This is an extremely faint object. 22nd magnitude is something almost impossible to see except with the biggest telescopes in the world. It's inferred if it reflected the same amount of light that comets do, it would be something like 62 meters in diameter. So this is sort of like football field scale object. Okay, so the point of this is there's no other object in the solar system that is this elongated, this flattish shape. Usually when pieces of asteroids come off, they're maybe 3-to-1 ratio, never 6-to-1 or 10-to-1 like this. Okay, so now this object, another very unusual thing was its trajectory. It got as close to the sun as 0.255 AU, at which point it was moving at 88 kilometers per second. And as it left the sun, the gravity of the sun slowed it down, so it won't stay that fast. The deceleration when it was at about 1.5 AU was measured to be 0.29 centimeters per second squared, which is a small deviation less than gravity alone would supply. So the sun is pulling on it, but it's only it's not slowing down quite as much as you'd expect if you just looked at the sun's gravity. It's about 0.1% less acceleration than you'd expect, and that deviation was pretty much a constant fraction of the gravitational pull, which tells you that that force that's acting on it, this non-gravitational force, is also varying with 1 over distance squared from the sun, like gravity. So comets do this. They have the exact same effect. And here's an image of the comet 67P from the Rosetta mission. And you can see that the part that's facing the sun is experiencing sunlight heating the ices. The ices are sublimating, turning to gas, and shooting off at the sound speed. And so it's just like a little rocket. And so you can imagine as this comet is going around the sun, there will be a force, and it's not a gravitational force, so this non-gravitational force pushing it away from the sun and keeping it from slowing down as much as the sun's gravity would like. But for comets, the effect is usually 0.01% of the pull and goes at about 1 over r squared. So Oumuamua was doing what comets do, but more. And that was a little hard to explain. All right. So a lot of these mysteries were compiled in a document by Loeb in 2018, and you know, these numbers, just to put numbers on it, they inferred there must be something like 4 times 10 to the 16 objects like Oumuamua ejected per star to have the odds. This is what they said, but to have the odds of one, you know, being detected in the solar system in those few years to be reasonable. So if you actually go through the math better, and the discovery paper by Meach et al. 2017 that described it, they went through the math better, and I can explain that if you want. But actually, the number you need is 7 times 10 to the 14 objects per star with some great uncertainties. Either way, it's kind of a lot. Our solar system has, we think, ejected about 10 to the 12 comets into our Oort cloud. So maybe there'd be a few times 10 to the 12 comets in interstellar space. So anyway, this is a big number, although we're talking orders of magnitudes, and it's hard to get a handle on these things. And as I said, it was moving relative to the local standard of rest at a relatively slow speed. You know, you might think if it's ejected from a star, it should be moving relative to the local standard of rest at 20 or 30 kilometers a second. And it was very elongated. Like I said, no solar system object was more than a 3-to-1 ratio. That push, it was like comets, but not like comets. And one other thing I didn't mention is that the Spitzer Space Telescope that observed it in infrared was able to, well, it didn't see anything actually when it looked at it. So you could place very firm limits on how much dust was coming off and how much carbon monoxide and carbon dioxide, and to some extent water vapor as well. So you could tell that it was not ejecting quantities of dust, CO, water, the way you'd expect a comet to. So these are all the mysteries of Oumuamua. So given that we had this data and nobody could point to a solar system object that was like this, there was a lot of speculation about what this object is. And they usually focused on one aspect of the problem or the other, and not try to fit all of them all at once. For example, the axis ratio, that elongation. And some ideas were that it was an asteroid that was tidally disrupted as it left its star, or perhaps you had some chunk of ice that was eroded while it was traveling through interstellar space. And an interesting thing about erosion is if you erode the same thickness from all sides per time, then comparatively the skinny part gets skinnier over time. It's kind of like a bar of soap. You have a non-spherical shape, and it gets exaggerated by the time you lose a lot of mass to a very elongated shape. So that's a viable idea. And of course, you know, it's this cigar-shaped thing. Maybe it's a spaceship. Yeah. So there's actually, I won't go through this slide. There's a whole bunch of ideas out there to explain these axis ratios. Another set of models tried to understand the non-gravitational acceleration. Why was it pushed so much compared to normal comets? And one of them was an idea out there that this is made out of a different ice than normal comets are. And this particular model posited hydrogen ice, which all I'll say about that is you would need temperatures of 2.8 Kelvin to freeze hydrogen into ice. And there's no place we observe that gets that cold. And there's theoretical reasons to think you couldn't, because you have the cosmic microwave background that keeps it from getting below 2.75. So there you go. And then one other idea that was expressed was this idea of a solar sail. So giving up on the idea that it could be an ice pushed by sublimation and outgassing, Loeb basically conjectured that it had to be pushed by radiation pressure, in which case it would have to be extremely thin, a big sheet of something less than 1 millimeter thick, and leapt to the conclusion that it had to be a solar sail of artificial construction. So basically aliens. So we'd like to examine this scientifically, though, and come up with an explanation that possibly involves natural processes. And so that led us to investigate this problem. And so first off, I want to point out that the size and the shape comes from the light curve. You have to match how bright it is at different times, because again, we can't take a photograph of it. We can only look at the brightness. And careful work by Meschenko in 2019 showed that, yeah, it was probably a pancake shape, and it had these axes, diameters, 113 by 111 by 19. And these assumed that its albedo was 0.1. Now that is the fraction of sunlight that is reflected by the object, and 10% or 0.1. That's a pretty typical number for comets and asteroids and things. So that was a reasonable number. But we started to realize that, well, we're looking at some sort of weird ice, and it didn't have dust, so it was probably shinier. And what would that do if you had a higher fraction of sunlight that was reflected? And one of the main things is that the area is proportional to 1 over the albedo. It's like a big mirror, and the shinier the mirror, the smaller the mirror has to be to reflect the same amount of sunlight. And so the diameter is proportional to the albedo to the -1/2, the area p to the -1. The rocket effect, that force, is proportional to the amount of sunlight that's absorbed, because that's what's heating the object, times the area. And so that is proportional to 1 minus p and times p to the -1. That's the force. And the acceleration is the force over mass, and the mass is proportional to the size cubed. And so p to the -3/2. And so when you divide by the mass, we found that the acceleration should scale as this formula, 1 minus p times the square root of the albedo. And so if you play around with different albedos, you can get a bigger push than if you assume that the albedo is 0.1. And again, most comets are dark. Maybe they have p as low as 0.04. They're really kind of like the darkest coal you can imagine. And that would imply that to reflect the amount of light they do, they have to be very large and heavy, and that would be difficult to explain how much they're pushed. But if you allow for the fact that this is probably a very shiny, icy object with an albedo greater than 0.5, fine, it wouldn't heat up as much, but there'd be a lot less mass that you had to push around. So we began to investigate, and by we, I mean my co-author, Alan Jackson, and and Alan is in the audience, I believe. So we started to investigate how much push you could get if you assumed different albedos or different ices. So we published this work in March in a pair of papers, and here's a formula we derived for the rocket effect. And all you need to know is that it matters what the ice is made out of, because it matters how much sunlight heats it, how much energy it takes to sublimate it. This is how much energy you're absorbing, and this is how much it's emitting, and so on. So we can calculate based on the ice and its properties and its albedo what fraction is absorbed and how much the ice sublimates and how much rocket effect you get. And so in this table, Alan did a great job of investigating the literature and finding all of these ices and the relevant properties. And we calculated the push. And it turns out that there's usually, okay, I'm trying to find, there we go. Okay, this is a graph of the acceleration that you get in units of the acceleration that is observed. And this is the albedo, the shininess of the ice. And we have different ices that are graphed here. So if you are made out of water, and you're on this trajectory at the bottom, it turns out that whatever albedo you assume, water isn't going to cut it. You do not get enough of a push from sublimating water ice to push Oumuamua as fast as non-gravitational acceleration seemed to be. If it were made out of neon, you would get a big push if it were made out of neon, but we can't even imagine a scenario where you would make an object out of frozen neon, So you have to kind of couple these with what's plausible. And hydrogen ice, by the way, would be an extremely effective rocket propellant, but it it also, like I said, it's hard to imagine how you would ever get it. And in fact, it would either have to be extremely shiny. It's like too good. It has to be extremely shiny or extremely dark. All these curves have a maximum and like a low and a high albedo solution. These are excluded, this purple band, by the Spitzer measurements. Comets are sort of at this end, but if it were really as dark as reflecting only 1% of the optical sunlight, we would have seen the infrared with the Spitzer Space Telescope. They would have to be ginormous. So we can exclude that. So we can pretty much exclude hydrogen ice from that basis alone. Yeah, so there's a lot of ices that are hard to justify their existence, but one that stood out for us was nitrogen ice. And it turns out that you could have an albedo about here or here, and 0.65 would be an appropriate albedo, so that if you had an object made out of frozen nitrogen, N2 ice, then it would get exactly the acceleration that you need. And what was really astounding to us is that this is an observed thing in the solar system. We know on the surface of Pluto, it's almost entirely frozen nitrogen ice, and the albedo of Pluto and nitrogen ice is in this red range. The best estimated value is right there. So right in that little circle is where you have the albedo of nitrogen ice and the albedo that we need, and the albedo of nitrogen ice on Pluto, and they are the same. So basically, if you were to take a piece of Pluto's surface and throw it past the sun as it went by 0.25 AU and went out, it would behave exactly like this object in terms of its dynamical trajectory. And also, it wouldn't have dust. It would have only tiny amounts of CO that are under the limits. It would conform to every expectation about Oumuamua based on observations. We could calculate, in fact, the trajectory of Oumuamua. This is the distance of the sun versus 0 here is the day it was first observed. Perihelion was a little before that. So it got close to the sun over the course of a year and then left the sun. Based on the idea that it's nitrogen ice, we could calculate all of these different properties, including its surface temperature. I'd like to point out, it's amazing. It stays under 50 Kelvin, even when it's inside the orbit of Mercury. And that is because of evaporative cooling. When you evaporate so much material so quickly, it carries heat away from the object. And I'm in Arizona, so if you have been in Arizona and gone into the swimming pool and jumped out, even if it's 110 out, the humidity is low, so you evaporate quickly and you're actually cold. I could actually be shivering on a day when it's 115 because of evaporative cooling. So the surface temperature remains as cold as the surface of Pluto, even though it is on an orbit inside Mercury. But the flip side is it is losing mass like crazy. And so its mass in terms of millions of kilograms starts here, but by the time it rounds the sun, it's lost over about 95% of its mass. And what is left when it comes by the Earth is just a sliver of what it used to be. And if you look at the axis ratios, if they started at around 2.4 to 1, which is something normal for fragments, then by the time we observe it, it's already in that range of about 6 to 1. And it's probably 8 to 1 now. So again, this explains the shape of it and the composition of it and the non-gravitational acceleration of it. So we're pretty satisfied that that's what this object is. It's a piece of ice just like Pluto. And yeah, this is just to show that the non-gravitational acceleration actually really does work out. And it's more like an r to the minus 1.8, which is actually very consistent with the data by Michel et al. All right. So we imagine that Oumuamua is a piece of a surface of a planet that is like Pluto, but of course it's not our Pluto because that would be in our solar system. This must be a Pluto in another solar system. And in fact, there must be a lot of these exo-Plutos ejecting fragments of nitrogen ice like this. But But if it were like our Pluto, if this is somewhat universal, then our Pluto has almost pure nitrogen ice on its surface, with CO, frozen carbon monoxide, being 0.1% of the mass, and methane being less than 1%. And again, these limits, I mean, it's not to say that every exopluto surface has to be the same, but if it were the same as Pluto, this would satisfy the upper limits from the Spitzer observations. Okay, so yeah, so let's talk about nitrogen, because actually we do see it in our solar system on the surface of Pluto and on the surface of Triton. We actually don't see it really in comets, and that's actually been a mystery for a long time. Why isn't there more nitrogen in comets? Recently, observations of 67P were used to infer that almost half the nitrogen is in the form of ammonium salts, and the other half is kind of in ammonia. So that seems to be the dominant form of nitrogen. It's in a solid form. And we don't see a lot of N2. It's maybe just a few percent of the total nitrogen. However, once you get this into a planet, it's pretty easy to convert it into N2. And so that's why Pluto is covered with it, but comets don't have it. So yeah, Triton's surface also big enough, let's call it a planet. It is covered in mostly N2 ice as well. As we look at the largest Kuiper belt objects, I don't know if you're familiar with this Rogues Gallery, but the largest Kuiper belt objects in the Kuiper belt are, Pluto, Eris, Haumea, Makemake. And we're very certain that Pluto has N2 ice, thanks to the New Horizons mission. The amounts of N2 ice on these other objects are hard to determine. It seems like they have some, but we can't put limits on it. But we would not be surprised at all if they also had nitrogen ice, in addition to Triton. So how does a planet do that? And again, by planet, I'm talking about a dwarf planet. But we think that on Pluto, it differentiated. It had enough radioactive elements in it to melt the ice enough that rock settled to a core, and it has a rocky core. And the rest of the ices form a water ocean, followed by water ice. And if there's geochemistry in this ocean, it's quite favored for nitrogen to be converted into N2, which is a gas which doesn't want to dissolve in that ocean. And so it would naturally erupt onto the surface and freeze there and form N2 ice. Now, right now, Pluto has an N2 ice crust that is a few kilometers thick. But based on how much nitrogen we think that all these planets are born with, it could have had one that was as much as 35 kilometers thick. And I didn't mention the other KBO that I'll be talking about a lot, which is Gonggong, which is named after a Chinese water deity. But it is about half the diameter of Pluto, so it's a useful thing to talk about. And it could have had an N2 ice layer of 18 kilometers thick. And these oceans and these crusts, they actually form pretty quickly. It could take at most 100 million years, but it could take only 10 million years to form these once these planets form. So it's probably a universal thing that a bunch of Kuiper belt objects have these N2 ice crusts. But now, how do you get them off the planet, and how do you get them into interstellar space? And to understand that, you have to understand something that we've only recently discovered about our solar system, which is that it underwent a huge dynamical instability early in its history. And we don't know exactly how early, but I think the consensus now is something like 50 million years after it was formed. And now it's 4,500 million years old. So this is in the first 1% of its lifetime. But when the solar system formed, most of the community accepts now that the giant planets actually did not exist where you find them today. Right now, you find Jupiter at about 5 AU and Neptune all the way at 30 AU. But when they formed, they were probably only between 5 and 15 AU. And in fact, probably Uranus and Neptune had they later switched places. But there was also this disk of material between 15 and 30 AU that we call the primordial Kuiper belt. And today the Kuiper belt has a total of maybe a tenth of an Earth mass of material in it. But when it formed, the theories can constrain it to have had something close to 30 or 35 Earth masses. of objects. So it's been depleted. And that's because when these objects get close to a planet, they can experience a gravitational slingshot. And we think this happened quite a lot. And in fact, they can be gravitationally slingshotted into a different orbit that maybe ejects them right away from the solar system, or just usually puts them in an orbit that lets them cross the orbits of the other planets. So if any of these objects had an orbit that crossed the orbits of these planets, then they could have an interaction with them. And it's getting all these gravitational slingshots. Sometimes that slows the planet down a little, and sometimes it speeds the planet up a little. And sometimes the planetesimal moves in and the planetesimal moves out. But over time, what's going to happen is that Jupiter is going to give enough of a gravitational slingshot to eject a lot of these objects. Some of them all the way out to interstellar space, most of them, and some fraction of them to a really big orbit that keeps it bound to the sun and populates what we call the Oort cloud. But over time, Jupiter is the one that gets rid of them. And so there's a sort of, I forget what slides I have here, but yeah, what happens is as these objects slingshot between the planets, Jupiter is usually the last planet to see one of these objects, and it slingshotted it out, and so its orbit moved in. The last time any of these planets saw a Kuiper Belt object is when they slingshotted it into Jupiter, and they tend to move out. And so over time, the orbits of Jupiter, Saturn, Uranus, and Neptune kind of move apart from each other. And Uranus and Neptune actually at one point got close enough to switch places. They scattered off of each other. And at a different point in time, Jupiter and Saturn got into a resonance where Saturn was going around once for every exactly 2 Jupiter orbits. And this just made the whole solar system go haywire, because Jupiter made Saturn's orbit become very elongated, eccentric, and then it started interacting with the other planets, and it just went crazy. So this whole process is what we think led to a few things happening. One is that Neptune migrated out quite a lot through this primordial Kuiper Belt and just scattered every object that it encountered in a gravitational slingshot, and it accelerated this whole thing. And you ejected a lot of this material via Jupiter into interstellar space, but maybe 20% of that material stayed in the Oort cloud. Only 1 part in 1,000 actually stayed in the modern day Kuiper Belt, where we see today. Many, like Pluto, were caught in sweeping resonance with Neptune, and you cannot understand the Kuiper Belt without this model. So it's really accepted today that this is what happened in the early solar system. But one thing I didn't appreciate until I started researching is that it's believed, therefore, that there were about 2,000 Pluto-sized objects and about 6,000 Gong-Gong-sized objects in this primordial Kuiper Belt. So we only have 1 Pluto today that we see nitrogen ice on, but there would have been thousands and thousands and thousands of these objects. And most of them were scattered out of the solar system, but not before they got hit with a whole bunch of other stuff. And that's kind of another part of the story. So yeah, the solar system ends up looking like it does today. And we populate the Oort cloud and populate many more times the mass of the Oort cloud into interstellar space. All right, so there would have been a lot of collisions during this stage. As all of these objects are being ejected by Neptune, or scattered by Neptune and ejected by Jupiter, the orbits of all of these Kuiper Belt objects are going crazy. And so we calculated how many collisions you should get and how much mass should be ejected by each of these collisions. So one thing is, these collisions are happening at a few kilometers per second. Every time an object like a comet or something hits the surface of a Pluto, it will eject material, mostly from the crust, and it doesn't go that deep. So it's mostly 2/3 of the time going to eject nitrogen ice, and 1/3 of the material that's ejected should be the underlying water bedrock. And most of the debris should be less than 100 meters in size, and that's really important. And it should actually have a very steep distribution of sizes where you have lots and lots and lots and lots of tiny fragments and very, very few big fragments, unlike the distribution of Kuiper belt objects themselves. But anyway, we calculated how much mass should be ejected during this stage. And this material would have gone into orbit around the sun and been ejected from the solar system by Jupiter, just like the other stuff. So if other solar systems are doing the exact same thing that our solar system did, they should also be ejecting considerable amounts of N2 ice. One last thing here is that N2 ice, could it survive passage from another solar system to our own? And we think that it would be eroded by galactic cosmic rays. These are these energetic protons and other particles that are zipping through space, and they hit the Earth's atmosphere, and that's why you don't want to spend too much time in a plane. These cosmic rays would erode nitrogen ice, and we based it on some laboratory experiments that were done to calculate that it would survive, maybe 1 or 2 billion years in the interstellar medium. So we used that to figure out how much it would be eroded, and that would probably flatten it somewhat before it got to the solar system. So we're kind of favoring that it started at a axis ratio, trying to make this bar go away, and I cannot see my slide. Okay, it would probably start at something closer to 2-to-1 axis ratio, and by the time it reached our solar system, if we're traveling about 500 million years in space, it would be at a 2.1 to 1, so a little bit more. All right, okay, advancing slides, thank you. All right, so let's get back to those mysteries now that we've got this model. And I'm going to list them and go through them one by one, see if we've explained it. And this first part, how many should be ejected? And it seems like, yeah, the number they quote it was 4 times 10 to the 16. It's actually closer to 7 times 10 to the 14, but it seems like a lot, right? But these fragments are all very small. And if you were to add up how many fragments our solar system ejected, we calculate something very close to this number of 10 to the 15 fragments. And they're each very small, maybe tens of meters in diameter. And so their masses are on this order. When you add it all up, it's about 3% of an Earth mass. So it's actually a very small fraction of the Kuiper belt, the primordial Kuiper belt, and not even a very big fraction of the nitrogen ice that existed. So that's actually not really a problem. And of course, there was this second object that was discovered a year after Oumuamua. The second interstellar object is Borisov, and that seems to be a normal comet. And indeed, there would have been about 10 to the 13 comets ejected, and that's kind of consistent with the appearance of Borisov in this time frame. So the numbers actually work out pretty well. What about that velocity with respect to the local standard of rest? Well, it turns out, yes, it's true that stars generally move at 20 or 30 kilometers per second relative to the local standard of rest, and our own sun is at about 18. But that's not true of all stars. And the difference is that young stars actually, and molecular clouds that they're born in, they actually have very slow speeds of about 6 to 9 or so kilometers per second with respect to the local standard of rest. It's only older stars older than about 2 billion years, that have these high dispersions, these high velocities. And that's because if you've gone around the galaxy 20 times or a few times, you're going to have encountered other stars, getting gravitational slingshot off of them. So yeah, most stars are older than 2 billion years, and they have these high velocities, but young stars do not. And so this points to the idea that Oumuamua came from a young stellar system. And indeed, in our own solar system, we would have ejected Oumuamua-like objects during the first 50 million years or so, so much less than 2 billion year lifetime. So that's actually not so mysterious. Right, so it probably came from a young star, and probably also has not been traveling for more than 2 billion years. All right, what about that axis ratio? And that's just really easy to explain if it were losing 95% of its mass as it went by the sun. And then we don't typically see objects do that, because we don't typically see nitrogen ice fragments, but if you had a nitrogen ice fragment like the sun, it would lose 95% of its mass, and that would increase its axis ratio. But it probably needed a little bit of help getting its axis ratio flattened a little bit before it entered the solar system. You know, fragments get up to 3 to 1. Some are 2 to 1, but a more typical number is more like 1.5 to 1. So if you need to get from there to 2 to 1 sort of axis ratio, then that would be consistent with it going through the galaxy for about 400 million years, 500 million years, and being eroded by cosmic rays. And we think that's a very interesting number because if you go ahead of the sun's trajectory in the galaxy, the sun was going this way towards Vega, and you go like, what's you know, 4.4 billion years of Oumuamua's travel upstream in that direction, and you realize it's the Perseus arm. And the Perseus arm would be a place where you would have a lot of young stellar systems. So you probably have a lot of just formed stars, just formed early solar systems, ejecting a lot of these nitrogen fragments. And they would have traveled about 500 million years before they get to our sun. And that seems to be consistent. This isn't necessary. This is a little bit speculative, but it all seems to hang together. All right, almost done. The non-gravitational acceleration, it's like a comet. It looks like outgassing, but it's stronger. But that is, again, because it's made out of nitrogen ice instead of water or other ices. So we think that that's all very satisfied. And the Spitzer infrared observations, no, it would not have significant amounts of water, CO, or dust because it's like the surface of a Pluto. And Pluto's surface does not have those things. But interestingly, it turns out, as red as the surface of Pluto. It's almost the exact same color. So we find it all very compelling. All right, so yeah, I think I already said a lot of this, but one nagging question is, all right, if our solar system and other solar systems ejected lots of N2 ice fragments, then why don't we see any in our own solar system? They should have been ejected into the Oort cloud. And so you should see, you know, maybe Oort cloud comets, some of them should be this N2 ice. And so we started to ponder that, and we realized that, yeah, we predict that 1 out of 20,000 comets should be, but and if you look at the larger ones, maybe 1 in 1,000 should be comets that are ejected from the surfaces of Pluto and the Pluto-like planets in our solar system. But here's the thing, that after spending 4.5 billion years in the Oort cloud, which is sort of almost a light year away from the sun at times, they would have been eroded by galactic cosmic rays. And so any small comets, fragments, would have been destroyed by cosmic rays. Only the very largest ones would survive for 4.5 billion years, the age of the solar system. But turns out there is one comet that might be the surface of a Pluto or a Pluto-like surface. This comet was discovered in 2016, and there's no water or OH detected coming off of it, and no sulfur species, and very little dust. And this is very unusual for comets, but it did have a lot of N2 and carbon monoxide, and it had this crazy N2 to HCN ratio, which is 10,000 times other comets, and it's about 3 kilometers across. And this blue comet was already identified as possibly coming from the surface of a Pluto or Pluto-like planet. And we calculate roughly about 1 in 1,000 comets should be like this, and that seems, from our model, and that seems consistent with the observations. So maybe there are a few things like Oumuamua, but only the very largest ones of them have survived in our solar system. So there you go. The first interstellar object discovered in our solar system, we don't think is actually so mysterious. In terms of its composition and trajectory, a chunk of N2 ice, like you see on the surface of Pluto, would be consistent with every constraint that we have. And the only question is how many of these fragments should we see and how probable it is that the first object we see should be one of these. And that's why we calculated how many objects would have been generated during the first few tens of millions of years of our solar system, but we find pretty good consistency between the numbers that are observed and the numbers we get. And so our interpretation is that Oumuamua is a piece of an icy exopluto that passed by Earth, and it's the closest we've ever gotten to a piece of an exoplanet that we know of. And be happy to take questions. Thank you for your attention.
All right, and thank you very much too. That was really cool. I never thought of Oumuamua being part of a Pluto-like planet. And we do have some questions in the chat, and if anyone else in the audience has questions of their own, feel free to add them in. I'll just kind of start back towards the beginning and work our way through some of the questions here. So Justin had a question. If Oumuamua came so close to us, within 0.16 AU, why weren't we able to take a picture of it?
Well, in a sense, we did take a picture, but we can't see the shape of it because we lack the spatial resolution. If you were to try to take a picture of a football field size thing at a distance of 10 million miles, that's what this is equivalent to. And you just can't make, in the biggest telescope can't get you the spatial resolution you need. There's just a limit to the optics, and this was way below that.
All right. Looks like the next couple questions are kind of similar to one that I had, and one of them seems to have possibly been asked by Oumuamua, according to the name there. That's strange. So were there any attempts to detect the outgassing? If this thing did lose so much mass as it rounded the sun, did anyone attempt to look for that, or was this something that you calculated after the fact and no one had a chance to look for it?
Oh, well, at the time, people expected that any interstellar object would be a comet. That was by far the most popular idea for what interstellar objects are. We think there are a lot of comets still, just they're probably outnumbered by these objects, but definitely outgassing was looked for. But the way you look for it is usually dust, and you see sunlight reflecting or scattering off of this dust. And so that was not seen, and you could put pretty tight limits on how much dust there was based on that. The other way is to look for spectral lines, spectral emission lines of the gas, and in the infrared usually, and that's how they could look for CO, CO2, and H2O, which are very common outgas species, and they didn't see those, so they could put pretty tight limits on those. Other things like N2 that might outgas, you cannot detect in the infrared. They just don't absorb in the infrared. So, in the same way, our atmosphere is transparent in the infrared except for the water vapor. So you have to go into almost the ultraviolet and look for it there. And I just don't think anybody happened to think to look at this with a sensitive ultraviolet detector, because it's actually very hard to do from the ground. So I don't know. I think it's an open question whether we could have detected N2, but nobody did, but I don't think anyone looked.
All right. All right, next question. Gregory is asking, if there is this enormous amount of icy mass being ejected by forming stars, should we ever expect to detect one of the interstellar dwarf planets themselves rather than their destroyed surface remnants? Or would that just be pretty uncommon and not very likely?
Well, it's a great question. I think it's so cool. And I think that the community is realizing that there are almost certainly lots and lots of rogue planets out there in the galaxy. They probably are almost as numerous as the stars themselves. So how would you detect it, though? These things are floating through interstellar space. They're as cold as the microwave background. And the odds of one passing through our solar system are basically zero. And I don't know how you would detect them, but they must exist. And it's kind of a spooky thought.
So most of them are roaming through interstellar space, too dark to see then?
Yeah. I mean, but for comparison, there were probably 10 to the 3 or 10 to the 4 dwarf planets ejected by our solar system in its early days, but there were closer to 10 to the 15 of these fragments ejected. So the odds are a lot higher that one of these fragments would come through.
Right. All right. Next question. Kaylin is asking, where do these names come from and how do you pronounce them? That's the first part of the question. So where did Oumuamua get its name from?
Yeah, so it's a Hawaiian word, and it was named in the Hawaiian language because the observations were taken with the Pan-STARRS telescope array on Mount Haleakala in Maui. And there's a growing recognition that we probably should honor the indigenous peoples who have held these mountains where we put our telescopes to be sacred. And in fact, anybody who's aware knows that there's quite an ongoing battle about how many telescopes should be put on Mauna Kea, and whether we have violated the agreement made with the Native Hawaiians or not. So I think it's a nice touch to give these objects names that reflect the language of the people on whose land these telescopes are placed. So yeah, and I don't know exactly. The little apostrophe thing is called the okina, and it's sort of a glottal stop. So to do it right, it's sort of like Oumuamua, but I won't butcher the language.
Now, I noticed the other interstellar comet, Borisov, was not named after
right. Comets are
Hawaiian.
named after their discoverers, 1, 2, or 3 discoverers, depending on how quickly they come in. And that was Gennady Borisov in Russia who discovered that using an amateur observatory that he built.
All right. Kaylin is also asking, how hard would it be to get to some of these planets? Or perhaps if we knew there was an interstellar visitor, how hard would it be to send a spacecraft to it to investigate it more closely?
Great question, and a really topical one. Now, part of the problem is if you want to go up and like land on this thing, then you would have to match its velocity, in which case you are going as fast that you would escape the solar system. And we don't know how to do that. It's just too hard to build a rocket that can go that fast. Nevertheless, we would really love to intercept these comets. And so there are ideas. There's the Comet Interceptor mission and a few other, that's the ESA mission concept, and Bridge mission. I'm trying to remember the names of the other mission concepts that are out there. But the idea is that you have a spacecraft in orbit kind of near the Earth, and it's ready to go. If we see another Oumuamua, we send it on a trajectory that would intercept, and they would necessarily just fly by each other at 50 kilometers a second or something like that, and our spacecraft would remain bound to the sun, and the object would go out. But at least you could get some maybe blurry pictures as it went by. No, I mean, they wouldn't be blurry, but you couldn't land on it, but you could at least see what it's made out of, get a spectrum of it, and determine what its composition is, etc.
All right. And Justin has another question. What is the largest size an object like Oumuamua could get while still retaining the same properties like velocity?
Well, yeah, we think that objects like Oumuamua that are ejected during impacts onto the surface of Pluto probably don't get much bigger than a few kilometers. Now, if you had one that was a few kilometers in size and you let it go by the sun, it would also outgas and it would get a push, but it's so much heavier. The non-gravitational acceleration would be much smaller, and probably you wouldn't even think twice about it. It's like it's going around the sun, that's gravity. You wouldn't worry about it at all. It was just that this is such a small object, smaller than just about any object we've ever observed in the solar system. And being so light, it had such a big acceleration from the rocket effect that we took notice of that.
All right. Looks like Kalen actually wants to leave the solar system. A lot of us agree with you, Kalen. We'd like to see what's out there too. It's just really hard to do, and then it's hard to get back. We would like to come home someday.
Yeah.
If only it were so easy.
Yeah, you better load up your MP3 player.
Yeah, if I imagine if we hitched a ride on Oumuamua, it would take us quite a while to get anywhere.
Yeah. So just for context, we act like this object passed through our solar system for 1 year. It was close enough to observe for less than a year. It's traveling for centuries. It's going to take centuries to get out past all the stuff in our solar system, and even longer, thousands of years to get out past our Oort cloud. I mean, it's just, our solar system is huge.
Another question popped up from Tim Martin. With the calculated quantity of these objects, do we have a projection as to when statistically we may see another?
Fantastic question. Yeah, that's sort of the number one thing. If we see them like with the same technology that we have today, if we were to see one a year, for example, then I think that would rule out my model, our model, because I don't think you can generate that many. The rate at which we would expect pan-stars to observe objects like this is once every few decades. So on the other hand, there is a new observatory coming online in about a year, a new array called the Vera-Rubin Observatory, that should be a lot better. And surprisingly, it's going to be able to see things that are so much fainter, and it's going to look at the whole sky every night, and it's petabytes of data. And well, we're involved in trying to figure out the occurrence rate, but I'm just guesstimating a few a year would be the number we'd see. So once that goes online within a few years, I think we'll have some better idea of the statistics and what these objects are.
All right. And so your prediction then is that more of them would be nitrogen ice objects rather than comet-like objects?
Yes.
From this model.
There's a few biases in that, because among the small fragment things, we think most of them would be nitrogen, not as many water, but it would look like even a higher percentage are nitrogen because they're shinier, higher albedos than the water. But none of them would have really big comas like comets do that you could observe, and none of them like dust flying off. So it was barely visible to us when Oumuamua went 0.16 AU close to the Earth. Whereas in contrast, an amateur astronomer discovered Borisov with his observatory when it was over 3 AU away from the Earth. So it's a lot easier to see comets. So I think we'll continue to see comets at a very rare rate of a few per decade, or I mean, every few decades. But it may be that we'll see a lot of these nitrogenized fragments with the Vera-Rubin Observatory.
Has anyone done the kind of back calculations on Borisov to think about how long it might have been in space or in what direction it might have come from?
Yes, and I'm trying to remember those numbers. Yes, people have done this. No, you can't identify it with a single star, and it is moving at a pretty high velocity with respect to local standard of rest. So I think the idea is that it's probably been traveling for billions of years, maybe.
All right. Well, that exhausts the questions in the chat. So if there are no more, then I would like to thank you once again for appearing with us here at Guilford Tech for this special event.
Well, thank you, Steve Desch.
Thank you, Steve Desch. It's been a pleasure to see my my doppelganger.
Likewise. I really hope we meet in person. But again, yeah, and I'm sorry I couldn't bring the beard. I couldn't find a beard to wear. So
I forgot about that too.
All right. Thank you, everyone.
All right, and thank you everybody for coming by. And don't forget our public nights. And students, don't forget to write this up for your extra credit.